So today we are going for the experiment number 8. So Shastri sir will explain you the experiment number 8. Sir, you can go ahead.
Okay, sir.
Just do the full screen in a slideshow mode. Yes, sir. Thank you.
So I said that experiment number 8 is similar to your experiment number 1, but the entity which we have to analyze and we have to draw a conclusion, that is different. But it is on the similar line. The first experiment was on a transmission line that was a microstrip line. And the second one is once again a printed transmission line, but it's a strip line, not microstrip line. Okay, so there is a difference between them. Now the difference is what? If suppose if you look at the microstrip line, then it's a 2-conductor transmission line, whereas your strip line, it's a 3-conductor transmission line, out of which 2 are grounded and 1 is responsible for carrying the signal from one point to the other point, unlike your strip line transmission line, where only 2 conductors were there and one it is used for the reference purpose, that is, it is always grounded, and the one is used for, one is responsible for taking signal from one point to the other point. Okay, so but what is the reason that why we are having so many transmission lines actually? Okay, so it totally depends on the kind of requirement. Like if you look at, and of course, one is having the advantage over the other. That also is the reason why we are having number of transmission lines. Like this strip line is better than any other transmission line. If you look at the structure here, then this transmission line is simply the modification of your coaxial cable. Coaxial cable is considered to be what? Superior most transmission line. The simple reason is that it does not have this radiation loss. Radiation loss, of course, up to certain upper frequency, the radiation from the coaxial cable is 0. But if you are crossing that upper limit, then the radiation may take place. And if not the radiation, not radiation actually, but the losses in the dielectric material. So you can have a coaxial cable which can support 10 gigahertz or larger than 10 gigahertz signal. But of course, the kind of dielectric materials are used, they are very costly. So the cost is going to increase. Okay. And if you modify that circular coaxial cable into what? More rectangular structure, so it will appear something like this strip line. Okay, but of course side walls are not there. But in strip line, here side walls are not shown, but it can have side walls also. Okay, in order to avoid any radiation loss. So strip line is very near to your coaxial cable. That's why it does not include a radiation loss. So the losses which are available or which are existing in strip line, that is dielectric loss and conductor loss. Radiation loss can be neglected up to certain frequency. And if the shielding is done, means the side wall is provided to you, then the radiation loss is 0. You will have only dielectric loss and conductor loss. Okay. Now, if you look at the structure, so the issue with the strip line is what? Even though it is lossless, this transmission line, but the problem is what? You cannot integrate this transmission line easily with the electronic components. That becomes little difficult. And if suppose it is done, then troubleshooting after once the circuitry fails, then the troubleshooting becomes difficult because the circuitry will be available between the two dielectric material here. Okay, here between the top dielectric material and the bottom dielectric material. There is the issue. So once the fault has occurred, you have to open it, you have to remove it, and then you have to troubleshoot and you have to fit all this. But same is not the case with microchip line, where this upper substrate is absent. You will be having this ground plane and this top plate. So the top plate, whatever circuitry we want to connect with the transmission line, all are available on the top surface of this bottom dielectric material. Since there is no second dielectric material which is covering the structure, all the components are easily accessible. And if any fault occurs, then it is easily traceable and we can troubleshoot it. That is a advantage. Okay. So now our goal is what? Actually, we have to the way we have performed in the first experiment. Here also we have to work on this different cases, like what is the, if B, that is the height of this strip line, is kept fixed, then width is kept fixed, then what is the impact of what this W? If it increases or decreases, then what happens to the characteristic impedance of the line? That is one parameter. Okay. Second, like varying A, what kind of effect you are going to get, and varying B, what kind of effect you are going to get. Okay. And once this experiment is suppose fully analyzed, you please mention in this conclusion whether the variation of this width of the transmission line and height of the transmission line and width of this central conductor, the change in all these parameters is it will result what? Change in the impedance. So this, the kind of behavior you're going to observe in this strip line, is it similar to the behavior of the microchip line? Okay, like in microchip line, if the W reduces, then the characteristic impedance increases. If B, there it was height, if that reduces, then this and other components are fixed, then the characteristic impedance increases. That kind of observation was done. So you have to compare the behavior of strip line with respect to the microchip line. That will be much better. It is expected. Huh? Wait, huh? Now we'll use the software. Okay, already we have used the software, line software. Okay, so once again we are going to use this software for the sake of analysis of strip line. Okay, so here you can see that there are this thickness parameter, thickness of the conductor that is there, width of the central conductor, then the dielectric material of the central conductor, and height H2, H1. Okay, so H1 and H2 will be taken separately. Like if the line is asymmetric in nature, plate, distance between the top plate and the central conductor, that is H2, is different than H1, then what happens to the characteristic impedance? Okay, and of course if H2 is suppose 1 mm and H1 is suppose 2 mm, so whatever impedance you will get, that will be similar to what when H1 becomes 2 mm and H2 is going to be 1 mm. Okay, so that will be there because of the symmetric structure. But of course, if H2 and H1 they are different, then what happens to the characteristic impedance, that we have to check. So once again, I will request you that you have to use the Excel sheet where you will be adding the parameters, and accordingly you will see what happens if one of the parameters changes and the remaining they are kept constant. So we'll start with the W and let's see what happens. You can have similar this dimensions, or you can have different dimensions than what I'm going to try now. So here, what I will do, I will first go for the symmetric case. Wait. Symmetric case means what? H2 and H1 will be same. So we'll take the standard dimensions. So I will start with H1, which is equals to H2, and that equals to okay, we'll take 0.4 because 0.4 I have seen this 0.4 mm thickness, 0.8 mm, then 1.6 and 3.2. These various cases we have to take. Okay, and after that, change in the dielectric material. So there are so many things to experiment. Okay, 0.4 I have taken. Next is of the copper sheet which we are going to use. So T. .35 micrometer. Okay, that we will take. This is the standard size. So if you are interested, you can have a thicker than this, that is 70 mm. Okay, these two I have the idea. 70 micrometer, then 35 micrometer, and then 70 micrometer. But generally 70 micrometer means the this what you say, high power engineering is required. Those who are dealing with motors, high power motors. For electronic engineering, it is not required. 35 micrometer is enough for us. That's why you can try either 17 micrometer or 35 micrometer. No need to go for 70 micrometer. 17 and 35. Okay, 70 is not required. It's not required for electronic engineering. Means those who are working at lower power. Okay, now we'll go for see already here this predefined value. So already I have chosen FR4, which is as per this software it is 4.7. So whatever is there, we cannot do anything. Any change cannot be made in this because FR4 means it has got a range 4.2 to 4.5 or 6 like that. So maybe 4.7 may be existing. This tan D and mu R can be changed. Mu R, it's here all the materials, they are not magnetic materials in nature. That's why mu R, okay, that should be kept 1. And tan D, that is loss tangent, that can be varied. So like loss tangent for FR4 is 0.002. Okay, so we'll see it later on. First, I have chosen FR4. Okay, so epsilon R is 4.7, mu R is 1. Okay, tan D is given here 0.025. So we'll take it as it is. Later on, if you want to modify it, you can modify it. Okay. Now we'll go for what? We'll experiment with W. Right? Thickness I have fixed, H1, H2. So here I will take 0.4. Okay. Now roughness, you can make it 0 or any random value you can have because tried it. Even though the roughness of the surface increases, there is no change in the parameter. So I don't think this part is working here. Once again, I will check it during this session only. Frequency of operation I have taken 1 gigahertz. Okay. Now, if suppose the width is, see, H1 plus H2, it becomes what? 0.8 if I add this 2. So in case of microstrip line, if the thickness is 0.8 mm, then for a 50 ohm transmission line, the width is 1.5 mm. Okay, so I will start from 1.5 mm and let's see what happens. Here it is different. It is 18.17 ohm. Okay, so I will write it here. W and impedance. Okay, so W is 1.5 mm, then impedance is 1.5. Now, if suppose I change it to 2 mm, oh, it reduces. It reduces actually. It has to reduce. It's 14.4. Any reason? Because you have worked on microchip line. So anyone knows why it is happening? Logically, because we don't want the mathematical answer. Anyone? Yes, anyone remembers? So for 2.5 mm, it is 11.9 ohm. Okay, so you can see that as the width increases, the characteristic impedance is going to drop. So if suppose I have to, generally the reference impedance is what? It is around 50 ohm, right? So if suppose you want to have a 50 ohm line, then what should be the width? So lesser than 1, let's see. Oh God. Okay. So if you are having width of 0.29 mm, 0.29 mm, then approximately you are having 50 ohm. That is 50.34, but 50 ohm we can consider. Now, if suppose you are going to manufacture, you are having the facility to manufacture microstrip line as well as the strip line, then which one you are going to prefer? Forget about the advantage of strip line over microstrip line. I'm talking in terms of what manufacturing this facility. Ease of manufacturing, you can say. Which one you will be preferring? Any answer? Hello? Microstrip line will be preferred or strip line will be preferred? Yeah, anyone wants to answer? Anybody? Aishwarya. Gagan Jain. Sanjana. Yes, B Division 33, Dharna Singh. Any answer? Too small actually. So if you go for manufacturing of this, it becomes really very difficult. So the cost is going to increase. But for the same dimension, if you are going for microchip line, then this width is somewhere around 1.5 mm. So that can be manufactured easily. Okay. So even though this strip line has got the advantage that the radiation loss will not be there, only dielectric loss and conductor loss will be there at that too, if the frequency is what too high. Okay, that depends on this loss tangent. Okay, so this is the impact of what width versus impact of the width on characteristic impedance. Okay, so if I plot this graph, there is something like this. So you can see it decreases here. I will go for that, or I can have it here. Okay, so we can plot it like this. All this you have to do. Okay, so now you can see that if the width is very, very small, then the impedance is larger. Otherwise, if the width increases, then the characteristic impedance reduces. And this relation is what there with all kind of transmission line. Okay, so if the width is very narrow, then the impedance is very large. Okay, so the nature of the graph will remain same for I think all the multi-conductor transmission line. But the issue is what? Whether this width for the same impedance, width of the main conductor for the same impedance is going to be different for a different transmission line. Otherwise, the graph, behavior of the graph is going to remain same. That is what? Width versus characteristic impedance. Okay. So this one graph is required. That is must. Then we'll go for the other parameter. As I said that if the line is symmetric, symmetric means what? If I divide this transmission line in two parts, and the reference line is suppose this width only, the central conductor. So the upper part and the lower part are separated by same gap, then the line is symmetric. But if suppose you are manufacturing a symmetric line, that is H2 is different than H1, then what happens? So that we will see. So what I will do, I will keep H1 as 0.4 mm and H2 as suppose that is 0.2 mm. Okay. Sorry, this time it is a variable, so I will keep it here. We are going to analyze the behavior if the line is what? Asymmetric in nature. Width I will keep it fixed. There is suppose 0.29 mm because it's a 50 ohm line. Okay. If H1 and H2 both are 0.4 mm. Okay. So I will start with 0.2 mm, then 0.4 mm, then 0.6, 0.8, then 1 mm, then 1.2, 1.2, 1.6. Okay. So these are the standard size, thickness of the dielectric material. 0.6 I haven't experienced. 0.2 is there, 0.4 is there, 0.8 is there, then 1.2 is there, 1 mm also is there, 1.6 is there, then 3.2. Okay. Now what happens to the characteristic impedance? So let's see. H2 I have to vary this time. H2 is 0.2 mm. So what happens? It must be H2 greater than or equals to H11. Okay, so I will do the reverse one. I will make 0.4. H1 is 0.2, suppose. So the impedance has got dropped from 50 ohm, it has dropped to 43 ohm. Okay. This is H1 and H2 is 0.4. Okay. So it becomes 44. So it's 43. I will keep increasing this. Let's see what happens. 0.4, you should get 50 ohm. Okay. So that we have got. Here it is 50 ohm. Now, if suppose H1 is 0.6 mm, then what happens? Point 0.1. So two ranges we have got when it is 0.1 and when it is 0.4. Okay, so when it is 0.1, so we get 38.45 ohm, 38.45 ohm, and for 0.4 is going to have 50 ohm. Okay, so it means that if one H1 is smaller than H2, or if the case is reverse, okay, H2 is smaller than H1, then in that case you can see that the impedance reduces, and when both are equal and the W satisfies the requirement of 50 ohm, then only it is going to be 50 ohm. Otherwise, for smaller thickness, the characteristic impedance reduces. This is one of the conclusion. Okay, so we have analyzed W effect of the variation in width on the characteristic impedance. Then having asymmetric this thickness of the line, that is when H2 or H1 is smaller than the other one, then what happens? Okay, and the next is dielectric material. Okay, so all these two relations, okay, width versus characteristic impedance, then height versus the characteristic impedance, these two. And next is what? Dielectric. When I say changing the material, it means that I have to change this material actually. Okay, one more thing you can do that instead of having asymmetric, the height, the influence of the height is not studied. Asymmetric nature that we have analyzed, height that we haven't seen. If both are, suppose 0.44, that is another case, when H1 equals your H2, then what happened to the characteristic impedance? Okay, so like for 0.4, we have seen 0.6 we are going to see, then 0.8, then 1, 1.2, then 1.6, 6. Okay, for which case for W equals to 0.29 mm. Okay, so when it is 0.4 mm, then we are knowing it is 50.34. But if suppose this increases, then what happens? So I will make this, okay, so 0.4, then 0.6, 0.8, okay, 0.6, 0.6. I think the characteristic impedance should reduce here. Okay, it is increasing. .76, 71, right? And if suppose it becomes 0.8 and 0.8, then what happens? It is 68.24. So it is increasing. For 1 mm, if both are 1 mm, 1 mm, so it is 74.13. 74.13. Okay, so here it means that if you want to have a larger characteristic impedance, then the thickness of the dielectric material should increase. Or what you can do, now see, you have seen that this increase in the thickness increases the impedance, okay, but the width is what, 0.29 mm. So I said that if you are going to manufacture it, then very precision instrument is required. Very the accurate instruments are required to manufacture, because 0.29 mm, it's very small width. Okay, so if you want to avoid such situation, so what you can do now, you can refer this characteristic behavior, that as the width increases, the characteristic impedance reduces. So what you can do, in order to have a larger width, that is W, and have a now in order to have a larger width, you can increase the characteristic impedance by increasing what? The height, H1 and H2. And after that, you can work on the width. Like if suppose I have 0.5 mm width, then what happens? Characteristic impedance has dropped. If I make it 0.7, okay, so it's 7.5. Okay, so you can see now the width is larger. Earlier it was 0.3 almost, means 0.29 mm. Now it is 0.75 mm. So 0.75 mm, you can go to any local manufacturer, and that local manufacturer can manufacture this transmission line very easily. But working at 0.29 mm, so even if a small change is occurring in the width, then there will be huge change in what? Your characteristic impedance of the transmission line, right? That's why this is the reason, see, why I'm insisting that you go for the analysis of multiple parameters. Why not one or two parameters? So here you can see that we went for what? The impact of width on the characteristic impedance that we have seen. Okay, so this gives the idea that if the width reduces, then only the characteristic impedance is going to increase. And finally here, if the height increases, then the characteristic impedance increases. So by increasing the height, you can increase the width to have characteristic impedance of 50 ohm at larger size of the width, which can be manufactured easily. Otherwise, you have to spend a lot. So you can save money. So we have done asymmetric, then symmetric line, then the effect of width, and the last one is dielectric material. So we'll keep this dimension fixed, okay, and we'll see what is the impact of epsilon r, okay. So I will write here width is 0.75 mm, and H2 both are 1 mm, okay, both are 1. Both are equals to 1 mm. If this is the case, suppose R, then the characteristic impedance is what? 50 ohm, right? Just now we have seen it. So characteristic impedance is 50, 51 actually, right? So if suppose I change the dielectric material, then what happens? So we'll reduce it because here we'll go with the smaller one, okay? So divide this 2.2, 2.5, 6 like that. Okay, so it is 2.2. Now I'll calculate the characteristic impedance. So it is going to what? 75.53. So if the dielectric material reduces, then the characteristic impedance increases. Next material, I will take Durate 550. So it should increase further. Okay. Now it has, okay, so dielectric material reduces, then the characteristic impedance for 2.2, it was 75.53. Now it is what? 2.5. So it is increasing, right? So if there is increase, then there has to be drop in the characteristic impedance, 70.86. Next is 6, dielectric constant, if it is 6 suppose, okay, which is larger than what, 4.7. So the characteristic impedance should be larger now. Sorry, it's smaller. Okay, for 45.74. Right? So larger dielectric material, so it's inversely proportional kind of thing is happening, right? I will keep it here. Okay, so that we can have a good graph, 45.74. Right? Where is this actually? Now last option which is available here. So it is epsilon 10. Okay, so semiconductor materials. Now if I calculate it, it's 35. Right? Okay, so let's have this. So you can see that now if as the dielectric material, dielectric constant increases, then the characteristic impedance, it decreases. Any reason? Remember any reason? Because you have learned this EME, right? Electromagnetic wave theory. So transmission line was taught there, okay? So from that, because characteristic impedance is what? Root of L by C. And C is what? Directly proportional to the dielectric constant. Means characteristic impedance is what? Inversely proportional to the root of epsilon R. So if epsilon R increases, then the characteristic impedance decreases, right? So that relation is seen here. So if I suppose plot a graph, right? Here. Okay. So you can see that as the dielectric constant increases, the characteristic impedance it decreases. So all this relation can be used for what? Designing correct transmission line for a particular characteristic impedance. So these analyses are going to help you if you are working in this area. Otherwise, of course, it is for the sake of knowledge, you can have it. Otherwise, those who are working, they know that if suppose you don't have such kind of information, then it takes a lot of time to design a correct device. So it becomes very time consuming. Okay, now if you have any query, you can ask. Otherwise, experiment part is almost, it is done. Okay, you have to just note down the kind of parameters which we are going to work on. First, keeping all the parameters constant, you have to demonstrate the relation between the characteristic impedance and the width of the transmission line. Okay, the asymmetric nature, but it has got limitation, that software, that this quantity should be larger or equals to this. So I think you can have more readings for this. Okay, it means what H2 is height of one substrate is different than the height of the other substrate. Okay, so that, and its impact on characteristic impedance. Okay, then next is the height, that is H1 and H2 both are increasing, or if they are varying, then what happens? So that relation I want. In that case, H1 and H2 both are going to be same. And the last one is what? Impact of dielectric material. Okay. So here, if you don't want to have this dielectric constant, or whatever is listed here, now you can change it. You can choose your own material, means you can define any random material A, B, C, D like that. You changed this dielectric constant, tan D, then mu R, all this can be changed, and you can please enter number between 1 and, okay, 1 I have entered. Cancel it. Okay, so if you want to work at some other dielectric constant, you can define your own constants and you can have the graph. Okay, but of course, whichever component or whichever constant you are selecting, the relation is not going to change. It is going to remain same. If the graph is of falling nature, it will be falling for everybody for similar kind of analysis. If it is increasing nature, then everyone will have the increasing nature of that graph. So the nature of the graph is not going to change. So everyone will have similar nature of the graph. And please write down the figure number and name below any graph or figure if you are adding, including in the write-up. The write-up for this particular experiment is available in the classroom. I have already uploaded it. I will upload it, you can ask.